Welcome to Unit 1, Lesson 10, Working with Complex Numbers. So before we work with complex numbers, we obviously need to define and understand what complex numbers are. And there's a definition right at the top and a great big table that or chart, I guess, that sort of lays all of this out for you. But before I actually talk about what complex numbers are, it's useful if I first talk about what real numbers are. So you'll see in this sort of branch here that we see complex numbers at the top, but it branches off into that one aspect of that is real numbers themselves. Now, real numbers are the things that you're actually used to in your regular math careers so far. So let's just look for a second at what real numbers are. Real numbers just are any numbers that could be represented somewhere along a regular number line. So a lot of those numbers are what we would call, for example, rational numbers. And those are any of the ones that could be expressed as a ratio of two integers, or in other words, like a fractional form. And so that's true of whole numbers for sure, but not just whole numbers, definitely integers, so positives and negatives, but also ones that have more complex decimals as well, because even a lot of complex decimals can still be represented as fractions as long as those decimals don't go on infinitely. There are other numbers, though, within that called irrational numbers. And those are special numbers like pi, for example, is one good example that you've learned before. And you might have heard that the digits of pi go on infinitely, and there's no pattern to those digits either. So it's kind of like they go on randomly and infinitely. And if you remember in our previous lesson, I talked about how certain square rooted values, like the square root of 2 and square root of 7 is another example, those are things that do the same sort of thing as pi. They have this random decimal expansion that goes on infinitely, which means there's no possible way to write those in any type of fractional form, and they're obviously not in the category of integers or any of those others. So they are their own separate type of number. But numbers like pi and root 2 and root 7, they do have a special place somewhere on the number line where they fit. So we know that pi, even though we can't exactly state what its value is, we know it's approximately 3.14159, etc. And so we can at least place and understand where it would be on a true, real, regular number line. Those are the real numbers. But we recognize that these real numbers aren't the only types of things that pop up in our calculations that we try and do in math. For example, I could ask you, where would the square root of -1 appear on our number line? Well, up to this point, you've just been told it's not something we can calculate. And in a sense, that's true. We can't really calculate what the square root of -1 is in a sense that we can't place the answer anywhere on the real number line. It doesn't equal a real number or a specific thing that could be plotted on a number line anywhere. But the square root of -1 is still something that pops up a lot in lots of calculations that we're trying to do. So it must still have some sort of mathematical value or mathematical purpose, and we want to find a way to hold on to that mathematical value and possibly be able to use it in future calculations. So we don't want to just give up when we get to the square root of a negative number. We want to be able to mathematically represent it and potentially be able to use it later on. So for that, we get into what are sometimes called imaginary numbers. So for imaginary numbers, we need a special symbol. And what makes them imaginary, again, is simply that they do not exist on the real number line, but they are still important in calculations. So we wouldn't actually see them appear on a ruler that you could measure or anything like that, but it's still important in calculations that might relate to length or something like that. And in order to hold on to this mathematical value, we need a symbol for it. So we define, we define the symbol I to mean the square root of -1. And what that literally means is that if I take this symbol I and I square it, it's equal to -1. And so anytime we run across this situation where we have the square root of -1, we just recognize that it will now be called the symbol I. And so that leads to what are sometimes called imaginary numbers. Again, so not just I itself, But we sometimes talk about purely imaginary numbers, like so, as maybe multiples of I as well. So for example, if I had 7 times the square root of -1, that would be 7I. If I had -3 times the square root of -1, that would be -3I. So I can actually use this concept of the square root of -1 in other mathematical calculations later on. But if my number is simply one single term with an I attached, we would call those purely imaginary. But where the complex part comes in is when we have a bit of a combination, because there are lots of imaginary numbers that are actually combinations of part imaginary pieces, but also real number pieces as well. So a complex number we can now define as follows. It's something in the form a plus bi, where a and b are just real numbers, but I is that imaginary unit. So what does a plus bi really mean? Well, it means there's going to be some number a, which is just a regular real number. That represents the real number piece of the complex number. But then it has this other piece attached to it that's got an I attached to it as well. So we might see a complex number that looks something like this one here. So it has a real number part of 4 and an imaginary part of 3I. Similar with this one. It has a real numbered part of 3, but it also has an imaginary piece to it of -2I. So again, it's not as simple as saying that some numbers are real and some are imaginary, because there are lots of numbers that actually have a real component to them. They have a portion that we could actually imagine plotting on a real line, but then they also have an imaginary portion to them as well. Now, in terms of picturing this and conceptualizing this can be really difficult to do. And so if you're still a little bit fuzzy on exactly what a complex number means, or exactly what an imaginary number means for that matter, that's okay for now. Because what we're really trying to stress in this lesson is how do we work with these imaginary units mathematically. That's really what mathematicians do. They often try not to stress too much about trying to picture or come up with a deeper philosophical understanding of what's going on. They first just try and see, can we mathematically work with these things in a way that makes some logical sense? That's what we're going to do for the rest of this lesson, is really focus on how do we do the calculations with complex numbers. So I'll do a few of these for you now. And we're going to actually just build on a lot of the same skills that we used in our previous lesson. So for example, the square root of 25, or sorry, the square root of -25 is what we're doing here. Well, I'm going to do my trick that I used in my previous lesson. I'm going to break 25 or -25 up into 2 separate radicals. So it's really going to be like the square root of +25 multiplied by the square root of -1. Now, if you're wondering why I did that, it's because now each of those separate pieces is something that I can mathematically calculate. I can say the square root of 5, or sorry, the square root of 25 is 5, and now I have a way to write the square root of -1. It's this little mathematical imaginary unit, I. So we would say that the square root of -25 is the purely imaginary number 5I. And I say that it's purely imaginary because it's only the symbol I with a number directly attached to it. There's no other whole number or real number piece attached to it by addition or subtraction. So this is a purely imaginary result. What about root 48? Well, root 48 itself can be broken up, but root -48 can be broken up the way that we did our previous one. So let's try root 16 and root 3, but also square root of -1. Now for that, I would get 4 and a square root of 3 and an I. Now, technically writing all of those and squishing them together would be correct, but just in terms of the conventions that we use in math, we always put the whole number or real number part first. So the 4 is definitely going to come first. And then we always tend to put the radical at the very end, which means I'm actually going to squish the I in between. So I'm going to actually just rewrite this as 4I root 3. So just keep that order in mind. Any regular whole numbers just go at the very front like a coefficient. Any radical pieces go at the very end. And then any i's can go sort of in between those. So 4I root 3 is a way that we can mathematically simplify and represent the square root of negative 48. Now notice that the square root of positive 48 would just be 4 root 3. So there's definitely a strong connection between the square root of positive 48 and the square root of negative 48. One is just the purely imaginary form of the other. And again, that doesn't mean that that number doesn't exist or is useless to it. It just means that it's not something that would appear on an actual ruler or an actual number line. But it's still something that we could use in further calculations that could help us with a real world problem. What about 125 and the fact that we have a negative as well? So I'm going to break it up into square root of 25 and square root of 5 and the square root of negative 1. So now technically I would, in my next step, I could write that as 5 root 5 and then I, but I'm just going to rearrange the order and write it as 5 and then I and then root 5. Just using that same order I discussed previously. Now I've got to be extra careful here because I have a negative in front of this whole thing, but I also, of course, have a negative underneath my square root sign. So I need to make sure that I keep this negative in front of everything no matter what happens. And then I think of it as the square root of positive 4 and the square root of negative 1. Or in other words, it would just be negative 2I. So now let's try a few more, and I'm going to start skipping some of these steps now. So now, if you've seen me do this a lot, you've seen that anytime I can pull out this square root of negative 1, essentially any time I notice that there's a negative inside of my original square root, in the end, it's going to just mean that I have this additional I attached to my final answer. So now we're just going to jump ahead in some of those steps and not necessarily always have to write square root of negative 1. So in demonstrating that, I'll show you what I mean with E. So for E, we would still have 3 subtract something, and now we just need to take negative 28 and break it up. Well, it's definitely going to have an I as part of it because we're going to use an I to deal with the fact that there's a negative as well. And then 28 can break up eventually into 2 root 7. So overall, I'm going to call this 2I root 7. And again, the 2 root 7 comes from the fact that 28 breaks up into 4 and 7, and then the 4 can be square rooted into 2. For this one now, similar idea. Again, I can't do anything with the negative 21, so I simply rewrite it, and then it's going to be added with whatever I get when I simplify the 98. So 98 can be broken up into, well, you might not have thought of this one at first, but it does break up into 49 times 2. And the only reason I choose to break it up into that way is so that I can get the smallest possible radical piece left over. So this would become 7I root 2. So because I broke it up into 49 times 2, I can square root the 49 to get the 7, and then I only have this very small radical piece of root 2 attached to it. That whole thing is still over 7. But all along, we can't forget some of those previous skills we've learned about simplifying by looking for common factors. So I can common factor out a 7 on top if I want to. So that leaves me with negative 3 plus just I root 2. All over 7 on the bottom. And because I have 7s on top and bottom, I can divide both the top and bottom by 7 to leave factors of 1. And in the fully simplified form, it's just, oops, let's do that in black. Negative 3 plus I root 2. And one more of that type. So now we have negative 12 plus, and I'm just going to call this 3i, because the 9 square roots to become a 3, and the negative part, when we square root it, just becomes that symbol I. And that whole thing is over negative 6. Now I'm going to try and do some common factoring. So for example, I could common factor out a negative 3 on top. Now, I could also just factor out a 3 on top if I want, but I'm going to factor out a negative 3 just so that it can help to reduce and get rid of the negative that I also have in my denominator in my final step. So I'm going to factor out negative 3, and that leaves positive 4 minus I. I'm factoring out a negative 3, all over negative 6. And then, as I mentioned, I'm going to divide both the top and the bottom, not just by 3, but by negative 3, so that I get positives on both the top and the bottom. So the top now is just that 4 minus I that I already had, and then I still have a factor of 2 on the bottom, and that's the simplest way that I can write that complex number. In the second part of this lesson, we're going to just take this a step further and look at some other calculations we can do with complex numbers.